Today, continuing with the design of the foundation, the next type of the footing that we will discuss today is masonry wall footing. Because in the field we are definitely we can see many structures which are of the masonry structures. It can be a brick masonry, stone masonry structures, where the connection between the superstructure, I mean, and the foundation pad is not monolithic like a RCC footing, but you have to transfer the load through the mechanism of spreading the foundations at the base and providing the PCC layer, or if the load is higher, then you can go for the RCC under the bottom of the footing. So this foundation is basically provided in many cases in the academic building, masonry buildings, in the house, in the houses also, in the offices also, and even in the RCC building where there is no columns, and you have to raise the wall from the base ground floor. In that case, you are going for the masonry or the separate footing. Basically, we have to assume certain things that the load is transferred to the UDL at the foundation level, and we are ignoring the effect of opening also. We are taking that as a full load. Similarly, the overlapping is possible when when the two walls meet perpendicular to each other or at any angle or at corner. That overlapping effect is ignored. Rather, we can increase the soil pressure. Normally, we are taking it as a UDL, but we can increase in case of the two reasons. When the footing is on one-sided, spread or the step footing, when it is provided one-sided, then we can increase the UDL by 35%, and we can increase the load by 70% when it is a corner of the footing. Then the effect of presence of the beam cannot be monitored in this footing because beam is directly resting on the wall, and we are not taking additional load, rather we are just taking the load of the slab and the wall. The backfill also, the factor of safety with the backfill can also be applied. Against bearing, we are taking the factor of safety as 1.5. Further factor of safety can be applied. So normally some of the engineers are designing it by thumb rule for 1 story, for 2 story, for 3 story, but it's better that if we can compute the total load and then decide the area of the footing and then decide the number of steps required in the footing. Basically, the design is not difficult because you just need the total width and number of steps of footing. For that, first of all, you need to compute the total load acting on the footing. The total load is basically the load. First part is the load supported from the coming from the slab, 385 into sum of the length, the clear span. Li is the clear span of the slab supported by a wall. Then the 1920, the density of the wall, into Hi into Ti, where Hi is the center to center wall height, Ti is the thickness of the wall, plus half into Li into Qi. Then it comes as the Li is already explained, the span that is supported by the wall multiplied by the partition load on the slab. So in this way you are computing the total load coming on the wall, partition load, wall self weight, and the super load from the slab. Now you can compute the from the total load, that is W here, you can compute the width. You know that the Total load divided by the bearing capacity, net bearing capacity, is the width of the footing. So the second equation on this slide, you can see that the approximate base width is W approximately, that is the base width, is equal to the 10W gamma 2. That load is computed, the total load multiplied with the 10, and gamma 2 is the corner footing. We will increase at 1.7 for the interior footing, we will use it 1, and 1.35 for the exterior footing. So gamma 2 is a factor also. And from this formula, the denominator here is allowable bearing capacity minus 10 times the depth of the footing from the plinth level. So we subtract the overburden from the plinth level, and D is the depth of the footing in this case. So that is a formula used for computing the base width. Now the base width approximately is computed, and from that you can compute the number of steps. Number of steps is that the total width of the footing is larger, of course, than the wall thickness. So in the figure you can see the wall thickness is T. The projected part on the footing is M for the concrete at the base of the footing is M, and the remaining width which is left is basically the steps. So W approx is the total width that is computed, minus T is the thickness of the footing, and minus MH. MH is basically this width of the MH is M is basically the number of overhang. PCC overhangs are 2 for interior footing and 1 for the exterior footing. So M are the number of the overhang of the PCC. It means that the PCC at the bottom is projected on how many sides? So it is projected on 2 sides for interior footing, and H is the thickness of the PCC pad. So you will subtract these parameters, and then to compute the number we would divide by the half of the brick wall. You know that the thickness of the step is also equal to 114 millimeter. The width of each step is 114. So first you compute that how much width is left at the numerator and divide by 114 to compute the number of steps. Now the number of steps are rounded up because it can be in decimal answer. So that's why the real base width will be computed now. The base width will be equal to the thickness of the wall plus number of steps into 114 plus number of the concrete projection into H. You know that what is the concrete thickness at the base is normally the projection also. Horizontal projection MH is equal to the total thickness of the concrete base. So in this way you can compute the total base width of the footing. These all are the parameters shown for the exterior wall footing and interior wall footing.
सॉरी सर, ये कॉर्नर फुटिंग का बता दें कि मैसनरी वॉल में कॉर्नर फुटिंग किस तरह होगी?
That is just like the same footing. I mean, footing is same because it's a wall footing. So corner footing is section of the footing is same. Just the load, you have to increase the load by 70% for providing the corner foundations. You have to increase the load of the 70%. But section, either if you can go on both sides, then it will be a left side section that is visible on screen. But if you can go on only one side, footing, then it is a right hand side section. Now the point is that when the wall load is quite high and you are giving for very high lab for some double triple story structure, you are giving the masonry things, then you know that the load is too high, there are the number of floors are also there. Then you can think about providing the RCC pad under the footing. So RCC pad is provided under the footing when the load is too high. And when you think that the PCC under the footing can be damaged, you can think about providing provision of the RCC pad. For RCC pad, the steps sometime not needed when you think that it is a two-story building and you are giving a very thick RCC pad. Then the spread footing, I mean the step footing, can also be avoided, and you can directly make the your wall of your required thickness. What is the critical section for if you have to compute the bending moment?
सर
Because
आरसीसी पैड देने का फ़ायदा क्या होता है?
definitely your PCC for heavy loading जो है वो आपका PCC तो नहीं sustain कर सकता, it can crack. When the bearing strength of the concrete provided under the wall is not capable or lesser than the total wall load, then you have to make the RCC pad, because RCC pad behaves like a rigid foundations. I mean, like RCC footing is basically is more capable of taking the soil pressure. That's why. So here the critical section of the RCC are shown. The left hand side section, which is a column, is if the RCC wall is there, the footing section will be at the face. But when the brick wall is there, the second figure, the critical section will be at this point between the face of the wall and center of the wall. And when the RCC pad is the steel plate is provided, then the critical section lies at S by 2. So it means that the second case is there for the masonry footing. So you have to compute the bending moment at this point. At this red line is shown. So until here you will take the load and compute the bending moment. Let's say this is the L length from this point to the free edge. This is the total length L that is used for the computing the bending moment, and bending moment will be computed by the similar way as you are computing in the isolated footing, like load pressure into span by 2. Pressure into span by 2 is the load, then press, then you multiplied with the L by 4. So in this way you will compute the bending moment. Now this is the example where you can see that this is not a frame structure actually. Uh, First you see the plan and you cut the plan at anywhere, you take the section, you draw the section of a, let's say it is a two-story house, and you take the section of a house at any point where all these three walls are visible. So then you can see that the left hand wall is a single story wall, the interior two walls, the interior wall is a double story wall, there is a parapet height of 1 meter, and exterior wall is also two-story wall, and there is a parapet height also present on that. So all these values are given: ground floor slab, the span of the slab, height of the wall, thickness of the wall, depth of the footing, allowable bearing capacity, and partition load are given. Now you can compute, as I have told you, that first step is to compute the load, next step is to compute the base width, next step is to compute the number of steps, and then revise the total base width. Now you can compute this load, that is 385 into Li by this formula. So you will use the total span length here. In Li is the clear span supported by the wall, and you can see here that this is Li, then 1920 height of the wall is 1.2 meter, thickness of the wall is, this wall is 13.5 inch thick, so 0.3242 meter, and in this way you compute the values. Plus the last step is zero point 0.5 into Qi is the partition load is 100, Li is the span length supported by the wall. So different span length, 6 and 5 meter are supported by the wall. Please mute your mics. Then the approximate width is computed. 10 into W total load into gamma 2, because this is an interior wall, so it is 1, and Q allowable minus 10 into, and this is approximate width. Then you compute the number of the steps which are needed, and you width minus thickness minus 2 into 100, and these are, and the final divided by the step width is 114, so 5 steps we round it up. Now the exact width is computed. So total thickness plus m, the projection of the concrete on two sides, plus h is the thickness of the PCC, plus number of steps into width of the steps. So 1.112 meter is the total width required for the footing. So this is the sketch for the masonry footing. For this given data, this given data, interior wall footing, these are the, this is the design of the masonry footing. If you feel that the same masonry footing should be converted into the RCC pad and you don't want to make more number of steps, then the same problem is solved with the RCC pad, but the procedure is somehow different, because the number of steps will not be computed now, and directly the width will be computed. First you compute the load W value, and from the W, the total load, you compute the approximate width, where W 10 W gamma 2 or Q level minus 10D, and this width is slightly rounded it up to 1.125 millimeter, multiple of 1 inch. Then you go for the thickness, and you have to compute now the allowable total load, factored load. So you take the load as a factored. We take it here average factor, because the load was as a whole applied, so average factor is taken, dead load, live load divided by 2, and then you take it, because this is an approximate design of the footing, and you take the factor load. From the factor load we compute the shear, and shear is, you know that the shear can be computed by equating the equation phi VC and VU. So phi VC equation is here, you can see on the left hand side, and is equal to the total VU that is acting at the face of the footing. So VU, you know, is a QU into L by 2 minus D. So then you can compute the D value. D comes out to very small, but minimum thickness that is recommended for the RCC pad is 9 inch. So it is 2 to 5 millimeter for the footing especially. So that footing is provided as a 9 inches. And then you go for the steel reinforcement. So steel reinforcement is WU, the total load into the span, the projected. This is a similar like isolated way, but it is on one side only, because we are designing it for the unit width. So movement in the footing will remain the WU into L square by 2 all the time, where L is the distance between the free end of the footing to the critical section. And then you know that L is B minus T by 2 plus T by 4, because this is the, I have told you, the critical section of the footing lies at the 1/4 of the wall thickness. So that is added. And then you can compute the moment. From the moment you compute the R value and rho value. And this rho is slightly larger than the minimum. So you will compute the AS required. But AS minimum is still larger than that, because AS minimum is 0.002 BH, and from this row it comes out to the row BD, that is lesser, and AS minimum is larger. So you will go for the minimum steel. Normally the minimum steel prevails in the masonry footing, 1-2 story masonry RCC footing. So then you have to also go for the longer direction steel parallel to the wall, that is also the 0.002 BH, because here we are using the grade 40 steel. When the steel is minimum, then it's better to use the grade 40 steel, but the reason is that is relatively less, having less cost, cheaper than the grade 60 steel. So then you go for number 13 at 280 millimeter in both sides. This is the required design. Now you will check for development length, that this bars cannot be curtailed before the development length. So how much development length is computed as 456, that is larger than 1 feet. But now you will see whether this space is available or not. So available space is the length minus 75, and you can now see that the space available is lesser. So you need the 180-degree hook, double hook, to provide this steel. So in this way you can make the hook at the end of the RCC footing. So that you can the development length critical section is at this point. So beyond the critical section, the bar length was, if you just provide at the bottom, it doesn't furnish the development length requirement. So you made the double hook for that purpose. This is the plan and section of the footing. You can also make the step above the RCC, but even if you don't make the step and make it simple, it's fine. And the thickness of the wall was 342 millimeters. It was larger than the conventional wall thickness, which is 2 to 5 millimeter. Then comes the here another short problem, that you should try working for the foundation design for this small office building. The given data is also the bearing capacity, the plan of the building, the section of the building, and the density of the material, and other detail of the roofing is given for the load computations. So try to compute the number of steps and the width of the footing required for this building. Thank you. If you have any question from the masonry footing, you can ask.